this chapter, we're going to be looking at polynomials and other functions. In this lesson, we're going to look very specifically at the characteristics of the graphs of rational functions.
All right, hi everybody. So we're going to take a look at the characteristics of the graphs of rational expressions, okay? Now, or rational functions here. And what we mean by rational function is something of the form p of x over q of x, okay, where p of x and q of x are both polynomial expressions. Except, remember the one thing here, you can't divide by 0. So what that means is we cannot allow values of x that would cause this function to go to 0. So here's the restriction, and this leads to, okay, restrictions on x. Whatever values of x would force q to go to 0, I can't use those. No good. Now, just for a moment here, let's take a quick look at some examples of some rational functions here. So here we got y equals 1 over x. I mean, that is your most basic rational function that we can get. This is the basic fundamental one here. Then we've got just some variations on it. You know, you can see a stretch there. You can see a translation. Okay, you can see the more of that. Translation down 3 here. Oh, it's getting more complicated. Now it's harder to identify some of those transformations that we've got in there. Same thing over here. But just gives you an idea of what rational functions look like. Okay, now we want to take a look at the basic function here. Make sure that you understand some of the characteristics of the rational functions so that when we start to transform them, you're transforming these characteristics. And here we go. If you were to go to your calculator, basically this is what you're going to get here. Now, you should know here that your calculator sometimes has difficulty when the lines get close to vertical. And sometimes you'll see your calculator stop graphing them. Okay, so this is where you've got to know more than the calculator, okay? You've got to be able to understand and recognize what you're seeing there. So this is what your rational function looks like, and it makes perfect sense here. Because remember, our value of x is in the denominator, and as x gets larger, the size of the fraction gets smaller. So that's approaching 0. Now it does that if you're using negative numbers as well. It just approaches it from below the x-axis. And if we're using values of x that are really small fractions, when you divide by a really small number, you get a really large number, okay? But you can't divide by 0. So here we go. So we've got, first of all, non-permissible values. Okay, add non-permissible value here. We've got x cannot be 0. And what happens near that non-permissible value here is that as the x approaches it from the left or the right here, then the absolute value of y gets really, really big. Basically, if you approach it from the right, it gets really big in the positive direction. If you approach it from the left, it gets really big, but in the negative direction. Okay? Now, the end behavior. So what happens as x gets really, really large here? So as we sweep kind of left to right on this graph, where do we start, where do we end here? Well, basically what we're doing is we're approaching 0. We're approaching the x-axis. So what happens here is basically we are in quadrant 3, and that sweeps over to quadrant 1. And in fact, we spend all of our time in quadrant 3, and then immediately flip over and spend all of our time in quadrant 1. Okay? Now, our domain, x, is going to be the set of x values such that x cannot equal 0. Okay, and then x is an element of the reals. And there are other ways we could write that, but that's fine. Your range, well, your range is actually going to be the same thing. Y can't equal 0 as well. Okay, and that's because no matter how large x gets, there is no value of x that I can plug in there that'll cause that fraction to become 0. Okay, you can go out as far as you want, never will. Vertical asymptote, okay, well the asymptotes here are both related to these restrictions here. Our vertical asymptote here will be x equals 0, and our horizontal asymptote is going to be y equals 0. Now it takes a little bit of getting used to here. The horizontal one is y equals, and the vertical one is x equals. Okay, that's just the way those lines work. That's how those equations work. But yeah, notice we normally associate y with vertical and x with horizontal, but it's not quite the way that works here. Anyway, I hope that makes sense. Okay, so Now what we're going to do is we're going to take a quick look at the asymptotes. Okay, so the vertical asymptote of a rational function here. So that's the vertical line. Remember what an asymptote is. Let's talk about what an asymptote is. Okay, the asymptote is a line or function that a graph approaches for large. Now, normally I would write this out a little bit longer here, but I'm going to run out of room here in a second here. For large absolute value of x or absolute value of y. Basically, what I'm saying here is an asymptote is a line that the graph gets closer and closer and closer to as you go really far away horizontally or really far away vertically, okay, or both for that matter, okay. It's just something that it approaches here. There is a misconception, and you come by it quite naturally, that says that you can't cross an asymptote. That's true depending on what it is. It is true for vertical asymptotes. You cannot cross, the function cannot cross a vertical asymptote, but there's a good reason for that. So rational functions, we got p of x and q of x, and they have no common factor. Oh boy, that is a key point here. In fact, that is one of the things that we spend a fair bit of time in this chapter talking about when we talk about rationals here. It can have no common factor. If it does, then something else happens here. So when they don't have a common factor, okay, then you're going to get vertical asymptotes corresponding to the non-permissibles. So the vertical asymptote is going to be expressed as x equals the non-permissible value. And it's got to be an equation, okay? If you just say, if I ask you, if I was to ask you up here, what's the vertical asymptote, and you just said 0, that's wrong, okay? That's not an answer that I'm looking for. You didn't phrase it right here. It would be like me asking, what kind of car does your father drive, and you went red. Well, that might be true, but that's actually not what I asked. Okay, if just to say throw out the number 0 doesn't answer the question. I need you to answer that correctly by giving me the equation of a line. So now a rational function can have several vertical asymptotes. So take a look at this one here, y equals 1 over x plus 2. Well, because x can't equal negative 2, the vertical asymptote is x equals negative 2. Here, we've written the denominator in factored form. And so I get two non-permissibles, x can't equal negative 3, x can't equal 1. So those are my two vertical asymptotes. And notice there's no common factors between the numerator and the denominator. Okay? So that's what you need to know about vertical asymptotes. Now, let's switch gears and talk about horizontal asymptotes. Horizontal asymptotes are, they are similar to vertical asymptotes in what they are, but they are a bit different here, okay? So a rational function can have several vertical asymptotes, but it can have at most one horizontal asymptote. That's not, okay, for what we're going to do here, that's true. That is true. But I don't want you walking away from this thinking that functions can only have one horizontal asymptote, because that's not true. Okay, it's just this particular sentence tends to push people towards a conclusion that's not 100% true here. But what we're going to look at here with rational functions, that's going to be true. You can have at most one horizontal asymptote. So the function of a graph does not cross a vertical asymptote. However, the graph can, it may, it is possible to cross a horizontal asymptote. Okay, now let's just take a quick look at what that might look like. Okay, you might have an asymptote, a horizontal asymptote that does this, and you might have a function that drops down and just gets closer and closer and closer to it. Perfect, that's my thumb up. Okay, here you can also get an asymptote that goes horizontally, and then what happens is the graph drops below it and then comes back up and approaches it from below. okay? You can also have an asymptote where it does this, where it wiggles back and forth across that horizontal asymptote. It touches it an infinite number of times. But what happens here is as you go further on here, the function does start to approximate that horizontal asymptote. Okay? It gets closer and closer and closer to it. As it crosses over, it goes, and the distance away from it gets smaller and smaller and smaller. So those are different ways that we might be able to approach asymptotes. Now, normally I would have a little story that I would tell about this, about the shocks of a car. You don't want your shocks to be doing this. You want your shocks to be doing this. And this is always funny. You can tell when a car's got old shocks here and they're wiggling because they hit a bump and they just wiggles and wiggles and wiggles. Yeah, you'll recognize that if you ever see it on the road here. Now, let's take a quick look here. When a rational function is written in this form where it's a over x minus h plus k, so what has happened here is we are getting, actually let's zoom in on this one a little bit. What we're getting here is a couple of transformations of the basic rational function. There's been a vertical stretch and horizontal translation. Okay, but I already know that if we're talking about the base function here, I already know that horizontal asymptote should be at y equals 0. So a stretch won't change that, a vertical stretch won't change that, horizontal translation won't change that, but a vertical translation will, because a vertical translation will take that horizontal line, that's that horizontal asymptote, and move it up or down. So that's the issue here. And because without that vertical transformation, because the horizontal asymptote is y equals 0, anything that I add or subtract is going to be the horizontal asymptote. So that's what we get here, okay? The k identifies the horizontal asymptote, and we would write it as y equals k, if it's written in that form. Now, if it's written in the form f of x equals p of x over q of x, and you've got like poly over poly, well, we do have a bit of a shortcut. There is a little rule that you can follow for determining the horizontal asymptote, okay? Got a shortcut, and we're going to explain it to you right here. However, everybody, this is, what we're about to show you here, everybody, this is not algebraic. And I can't overemphasize that this is not algebraic. And what I mean by that is, although this is going to let you immediately tell whether if you have an asymptote or not, it's also going to help you figure out immediately what that asymptote is. If you were asked on an exam to algebraically identify what the asymptote is, you could not use this right here. We are borrowing this rule here from a calculus class. Okay, this does not naturally pop out of the material that we've covered in this course. We're reaching forward and pulling this back. So now, here's the rule. If the degree of the numerator is equal to the degree of the denominator, then simply divide the numerical coefficients of the highest degrees by each other, and this will be the horizontal asymptote. Okay, which is probably a whole bunch of blah, blah, blah. It doesn't make sense. I'll explain this in a second here. I'm just going to read these things out. If the degree of the numerator is less than the denominator, then it has a horizontal asymptote of 0, y equals 0. And if the degree of the numerator is greater, then there is no horizontal asymptote. Now, normally, the way I would write this out would be something like this. If we've got a rational expression that is, let's say, a sub m x to the m plus dot 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 over b to, n x to the n plus dot dot dot. So I've got polynomial over polynomial, but this is my highest degree term here, this is my highest degree term here. And it doesn't even matter what happens afterwards. It makes no difference. Okay? Then what happens here is if m is bigger than n, if the degree of the numerator is larger than the degree of the denominator, and I'm going to give you an example over here, okay? If the degree of the numerator is larger than the degree of the denominator, so let's say you've got y is equal to 5x cubed plus 10x minus 1 over 4x squared plus 1,000. 1,000. because the degree of the numerator is larger than the degree of the denominator, what happens here is the numerator grows much, much faster than the denominator. Like a lot faster. Okay, and in fact, the larger the difference between the degrees, the faster it grows. And in fact, what happens is this one here dwarfs this one. It doesn't even matter about these other numbers. Okay, when you're talking, in fact, that's a good way to think about it. When x gets really, really big, let's say x is a billion. 5 times a billion cubed, well, just look at this. If you subtracted 1 from that, would it matter? Well, no. If you've got a billion cubed, and let's say you had $1 billion cubed dollars, and someone offers you $10 billion, would you care? Well, no. I mean, that's chump change compared to that. These are irrelevant. And when you compare these two right here, this is so much bigger that really what happens here is if you cancel those out, you get 5x over 4. Like you can, if you just ignore all the rest of the stuff and just look at that right here, that's basically this right here, approximately this, and this just gets bigger as x gets bigger. So there is no horizontal asymptote here. If m is less than n, and so let's say an example like that is, well, let's just flip the degrees here. So 5x squared plus 10x minus 1 over 4x cubed plus 1,000. Well, now, again, as x gets larger, this stuff over here means nothing. It's just the leading terms here that are important. And if I try to simplify that there, basically that reduces down to this. Okay, I've got a larger degree in the denominator, which means the denominator grows faster than the numerator. But if the denominator gets bigger and bigger and bigger, remember that means the whole thing gets closer and closer to 0. So what happens here is we get a horizontal asymptote at y is equal to 0. If the degrees are the same, so now that's like 5x cubed plus 10x minus 1 over 4x cubed plus 1,000. Well, once again, these terms over here don't mean anything when x gets really, really big. And if you just simplify what you're left with here, because the numerator and denominator grow at basically the same rate, I can cancel the x's. This is like 5x cubed over 4x cubed, and I can just cancel those. And you're just left with that ratio right there, 5 over 4. So what happens here is you get y equals, the asymptote is this number here, that leading coefficient, over this number right there, that leading coefficient. That is the shortcut rule for this. Okay, and I hope that makes sense. We're gonna apply it in the next little bit here, and I'm also gonna have to show you an algebraic method of finding the same thing. Okay, everybody, there are 2 methods that we will accept for you algebraically finding the horizontal asymptote. And personally, just going to say, I'll throw this right up front here. Personally, I like this method better. Okay, I think it's clever, and I can follow this along really quite easily here. So we're going to use the inverse function. So just recall that the inverse of a function is when the x and the y are flipped. But what that means is the horizontal and vertical properties get flipped on it when you're finding an inverse there. So this means there's an alternate way of finding a horizontal asymptote, and what we do here is we find the vertical asymptotes of the inverse. Okay, of the inverse here. So when you find the inverse, find its vertical asymptotes, those will correspond to the horizontal asymptotes of the original, and vice versa for that matter. Okay? So for example, for the function right here, f of x equals 3x over 2x minus 5, the vertical asymptote is 5 over 2. Now, I can tell, based on my above rule, that my horizontal asymptote, because the degree of the numerator is equal to the degree of the denominator, they're both linear, following my rule here, this is what's going on, I know it's going to be the ratio 3 over 2. So I know this. Okay? I know this. I must prove this, or I must show it. Okay? I can't just state that and give the above reason and as my evidence as to why that works. So here we go. We're going to find that popping out using the inverse. The next page here. So first of all, we're going to interchange the x and the y. So that's going to get us x equals 3y over 2y minus 5. Actually, let's zoom in on this. Okay, so there's my inverse. I flipped the x and the y. Now we're going to isolate the y. So to do that, I'm going to multiply through by the denominator. Okay. Now I'm going to distribute the x through. So that's why I'm getting 2xy minus 5x equals 3y. I want to isolate the y. Okay, I'm finding the inverse in almost every case when you find the inverse, you isolate the y. So I'm going to bring the y term over, bring the 5x over, factor out the y, and then divide. So I'm going to get 5x over 2x minus 3y. So this right here, this is now, and I can't believe I'm writing this again. It's right below there. I don't know why I did that. This is the inverse function. So now let's take a quick look at this. What is the non-permissible here? Well, 2x minus 3, I can't allow that to be 0, which means 2x can't be 3, which means x cannot be 3 over 2. That's my non-permissible value. So that's my vertical asymptote for this function. And therefore, the horizontal asymptote of the original must be y equals 3 over 2. It's a beautiful little relationship here, and we'll accept that as your reasoning for determining what the horizontal asymptote is. Okay, everybody. So with this method number 2 here, what we're going to do is we're going to convert the function into a form where the transformation is a little bit more obvious. So we're going to take rational in the form of p of x over q of x, and we're going to turn it into this form a over x minus h plus k. So let me show you how that would look here. So we're going to take 3x plus 1 over x minus 6, and we're going to convert it into this form right here. Okay, so now what I need for this to work here is we need a common factor of x minus 6 in the numerator. Okay, so I need to be able to find an x minus 6 up here in the numerator. Well, I've got a 3x right there, so don't worry about the 1 right now. I've got a 3 in front of the x here, so if I wanted to have a common factor of x minus 6 numerator and denominator, I would need to have a negative 18 in the numerator. Okay, so it would be like 3 multiplied by x minus 6. So that's what I got to do. I got to take that negative 18 and I got to put it in the numerator. So that's what I do here. But just putting a negative 18 in there changes the value of the expression here. So what I got to do is I got to balance that by adding 18. So right here, the overall change to the expression is 0. I haven't done anything. Okay. Now I can split that up. So I can take my denominator and I can distribute it to this binomial and then this, well, it's not really a binomial, but those two terms there as well. And what that gets me here is 3x minus 18 over x minus 6 plus 18 plus 1 over x minus 6. Now factor out the common 3, put those 18 and 1 together, and then this cancels here is going to give me just a 3. And then over here, I'm getting 19 over x minus 6. Now I can reorder that so it's in a form that I'm more comfortable with. And then right there, I know that my horizontal asymptote is going to be y equals 3 because I can identify what the vertical translation is. Okay, so the big idea with this one right here is I'm trying to get an expression equivalent to this one up in the numerator, or some expanded form of it, right? I just want to be able to take out a common x minus 6 here. So because I see that coefficient right there, I'm going to run the coefficient through here and add that constant to the numerator so I can factor it out and cancel. So it's a little bit of work to make that work there. But you can do that. And now you can choose either method you want, either using the inverses here or converting it to a function where you can see the transformation a lot more clearly. Okay, so let's take a look at a question here where we're identifying the asymptotes. So this is 3 over x minus 2, so we're looking at a basic rational that's been translated. So it's been translated 2 units down, so that means my horizontal asymptote here is going to be at -2, and my vertical asymptote will just be where this is undefined, and that is going to be at 0. So those are my two asymptotes. For this next one, now I can tell right off the bat that my horizontal asymptote is going to be 2 over 1, or just 2. Okay, so y is equal to 2. And I know that because the degree of the numerator and the degree of the denominator are the same, so it's just going to be the ratio of leading coefficients. Now, just so that we do a little bit of practice with this, I'm going to take a couple seconds here and I'm going to quickly find that horizontal asymptote using the two different methods here, because this is really the type of problem that you're going to use that for. For the other ones that we've got here, you're not, and neither are you going to be really expected to. So let's take a quick look at this one here. So first of all, let's do it by finding the inverse. So I've got y is equal to 2x minus 1 over x minus 7. So let me just walk you through that real quick. So that would be x is equal to 2y minus 1 over y minus 7. So I'm going to multiply up, and that'll get me xy minus 7x is equal to 2y minus 1. Okay, now I'm going to bring the y terms over. And I'll bring the x term over. Factor out the y. Okay, equals 7x minus 1. And then when I divide 7x minus 1 over x minus 2, I'm going to get that this has a non-permissible, okay, an NPV, x can't equal 2, which means the vertical asymptote here, the vertical asymptote is going to be x equals 2, which means, okay, the horizontal asymptote of the original function must be y equals 2. Now let's use that other method that I showed you. Okay, so again we're starting, and we're going to look at this in terms of transformation. So we're starting with y equals 2x minus 1 over x minus 7. What I want in the numerator is the ability to cancel out the x minus 7. So I want to put that x minus 7 up there. Well, there's a 2 in front of the x there. So what that means is if I want to put the x minus 7 up there in an appreciable way here, what I need to do here, well, basically, actually, you might think of it like this. What I want to do here is take that 2x. If you multiply the denominator by 2, you're going to get a negative 14 there. Well, I can't just add a negative 14 there. Put a negative 14 there. I have to add 14 to cancel that out. And so then this becomes y equals 2x minus 14 over x minus 7. And then this is 14 minus 1 over x minus 7. Well, that's 2x minus 7 over x minus 7 plus 13 over x minus 7. Those will cancel, and when I put the terms in their proper order here, I get 13 over x minus 7 plus 2. And so now, once again, I can see that the horizontal asymptote has got to be 2, okay, or y equals 2, because that's the the vertical translation that I get. Now, anyway, so that's done. Here, it's undefined at 7, so my vertical asymptote will be x equals 7. Now, for the rest of these, we want to get you through them even quicker here. So for the horizontal asymptote, the degrees of the numerator and denominator are the same, which means nothing else matters, and it's just going to be the ratio of the leading coefficients. So my horizontal asymptote is going to be y equals 1. My vertical asymptote, on the other hand, I'm only going to be able to get that once I have done some factoring here. So the denominator is going to become x plus 3. I know that's x plus 3 squared. So now let's factor that numerator, and that's going to be x and x. And I want two factors that are going to give me a product of 12 and add to get negative 7, so it's got to be negative 3 and negative 4. Now, the reason why I had to do that is because if I could cancel that out there, okay, or if I could cancel something out, then I got to watch out what that means. Now, in this case, nothing canceled out here, but I want you to be aware of that going forward, that you should be factoring both the numerator and denominator when you do this. And so here we're going to get x equals negative 3. It shows up twice. It's the same thing both times there. Okay, the next one. 3x plus 2 over x squared minus 9. Now notice that the degree of the denominator is larger than the numerator, so the denominator is going to grow faster, and that's going to cause the whole thing to get small, the value to get smaller as x gets larger here. So I'm going to get a horizontal asymptote at 0, And now here, to get the vertical asymptotes, I have to factor the denominator, but that's a difference of squares. And so I know I'm going to get two vertical asymptotes at -3 and one at +3. In this next one, okay, still got to do a little bit of factoring here. In my numerator, I'm going to take out the 5, and I'm going to get x squared minus 4. And in the denominator, if I take out the common 2, I'm going to get x plus 3. Well, that's going to get me 5x minus 2x plus 2 over 2x plus 3. Okay, nothing's canceling, so I'm good with that. Okay, now that means that my vertical asymptote is going to be x equals -3, looking at the denominator where it makes it equal 0. And I can go up here and just take a look. Because the degree of the numerator is larger than the denominator, okay, there is no horizontal asymptote. Okay. Now, and finally over here, notice that there is no value of x, there's no variable x in the denominator, so that means there is no place where this is undefined, so there's no vertical asymptote. And then because the degree of the numerator is larger than the degree of the denominator, the degree of the numerator is 1, the denominator is 0, there's also no horizontal asymptote. And that's how you'd interpret it. So don't let us throw you off when we give you an expression like this. This is really just a polynomial. I mean, this is a line with a slope of 1/7 and a y-intercept of 6/7. Okay, you can just distribute that denominator to both those terms. Okay, now for this question, we're just being asked to complete the table. All right, here's the table. We can get that all in there. So we're going to get the characteristics of these three rational functions. So the vertical asymptote is going to occur where the function is undefined. So here, this is going to be undefined when x is equal to 0. Here, it's going to be undefined. I just got to make sure that nothing cancels there or wherever. It's all kind of clean, and that's good. So this is going to be undefined at 7. Oh, shoot, that's not what it's asking for. It's not asking where it's undefined. It's asking for what the asymptote is. And so that is going to be x equals 7. And here the vertical asymptote is where it's undefined, and that's going to be at +2. So x equals +2. Those are our three vertical asymptotes. Now, that corresponds with the domain. So the domain is going to be the set of x values such that x is not 0. X is an element of the reals. Here, x such that x cannot be 7. X is an element of the reals. Here, the set of x values such that x cannot be 2, where x is an element of the reals. Okay, so there's a link, a very, very definite link between the vertical asymptote and the domain. For the horizontal asymptote, well, here, that vertical stretch isn't going to change the horizontal asymptote, so it's still going to be y equals 0. Here, the degree of the numerator is the same as the denominator, so it's just going to be the ratio of the leading coefficients, which in this case is going to be 2 and 1. So this will be y equals 2. Here, because of the way it's written here, the horizontal asymptote, in that case, if you didn't have the -3 there, would be at 0, and that's been moved down 3. So the horizontal asymptote is going to be y equals -3. Now, for the questions that we're doing specifically in this chapter at this time here, we're going to assume that the function will not cross the horizontal asymptote, even though that's not a general rule. So our range here will be the set of y values such that y doesn't equal 0, y is an element of the reals. The set of y values such that y doesn't equal 2, y is an element of the reals. Set of y values such that y does not equal -3, y is an element of the reals. And there we go. And so now we're establishing a really strong connection between the horizontal asymptote and the range. The x-intercept is going to occur when y is equal to 0. Okay? Now, finding x-intercepts almost always requires solving an equation. So let's take a look at that first one. 0 is equal to 4 over x. Now, if I tried to bring the x up so I could solve for it, I would multiply both sides by x and I would get 0 equals 4. And then I'd sit there and go, what? Okay, well 0 doesn't equal 4. There is no solution to this. There is no x-intercept here. And that actually makes a lot of sense because my horizontal asymptote is the x-axis. And based on how we're going through this, it's not crossing that axis. So no x-intercept here. For the other one, so the next one here, we're going to let y equals 0. 0 is equal to 2x minus 1 over x minus 7. Same thing, I'm going to multiply through by x minus 7, but x minus 7 times 0 is just 0. And now I just got to figure out where this goes to 0, and that's actually pretty easy. I'll bring the 1 over, divide by 2. Oh, so there we go. So I've got an x-intercept here of 1/2. Over here, same sort of thing. I'm going to let 0 equal 6 over x minus 2 minus 3. A little bit more work involved. I got to bring that 3 over first. Then multiply up, and that will be 3x minus 6 is equal to 6. Bring the 6 over, and I'm going to get 3x is equal to 12. X is equal to 4, and there's my my x-intercept. Okay. Y-intercepts, on the other hand, are a lot different. Y-intercepts are just about evaluating the function. So if you just put 0 into here, I get 4 over 0. Well, okay, there's no y-intercept. That's just undefined. And that makes sense. Again, x equals 0 is a vertical asymptote. If you make x equal to 0 here, basically what happens is those two terms disappear, and I'm left with -1 over -7, or just 1/7. Over here, it's a little bit more complicated than that. If I let x go to 0, that goes away. And so now I've got 6 divided by -2. That's going to be -3. Minus 3 is going to be -6. Okay? And there you go. We filled in the chart. Okay, now for this question, we're going to look at the graph and come up with the equation in this form with the transformations in it. Now, I know that h and k, the way they show up right there, are going to refer to the vertical asymptote and the horizontal asymptote kind of respectively there. So my first graph right here, I can see that it's got a vertical asymptote at x equals 2, and it's got a horizontal asymptote at y equals 3. So without me putting in hardly any effort into this, I know that the equation has to be y equals a. There's going to be a vertical stretch in there. I don't know what that is yet. And then to force it to have a vertical asymptote of x equals 2, this is going to be x minus 2 down here. And then the horizontal asymptote corresponds to the vertical translation, so it's easy enough. I just put +3. Now what I'm missing is the vertical stretch. But that's easy enough, because all I got to do is pick a point on there, and you're going to see here that we've tried to make your life a little bit easier by identifying a couple of points that it goes through. And in fact, I'm going to use the one with the smaller values here. That's the point 1, 2. So if I plug that in, y is 2. That's going to be equal to a over 1 minus 2 plus 3. Well, the first thing you're going to do is bring the 3 over. It's going to be -1 is equal to a over, that's also going to be -1. Oh, and so we get that a is equal to 1. So that means that my equation is now going to be y equals 1 over x minus 2 plus 3. That's it. Over here we do a similar sort of thing. Here, my vertical asymptote is going to be x is equal to, looks like -2. My horizontal asymptote is going to be, what is that? Y equals -4. And so right off the bat, I know that this has got to be y is equal to a vertical stretch over x plus 2 minus 4. And now, same thing. There's a couple of points that were given that they're trying to imply by that I can trust those points here. So I'm going to use the one with the smaller values. Again, it's -1, -1 right there. And so -1 is going to equal a over -1 plus 2 minus 4. Bring that over, and I will get 4 minus 1 is going to be 3 is equal to a over 1. So a is equal to 3. Well, that's easy. So that means my equation is y is equal to 3 over x plus 2 minus 4. Okay, well, just like any other kind of function that we look at, there's always going to be equations that we're going to have to solve that are of that form. So we're going to solve rational equations. But the expectation right now is that we're going to do it graphically. Okay? You would have looked in a previous course, you would have looked at how to solve these things algebraically. And that's awesome, and I'm glad you guys know how to do that. But right now the expectation is that you're going to be able to use your calculator to do this. And so there are two ways that you can solve a rational, any function really, using your calculator. One way is to move everything over in that function to one side of the equation, setting it equal to 0. You graph that, and you look for the x-intercepts, because the x-intercepts will correspond to the roots or the solutions. Okay, we know that. Another way of doing it is to treat it more like a system of equations where you've got the left side of the equation equaling the right side of the equation, so you graph them separately in y1 and y2, and then we look for the points of intersection. And what we're looking for here is the x-coordinate of the point of intersection. The y-coordinate isn't relevant in that particular case here. It's really just the x-coordinate that we're interested in. So anyway, let's take a look at a few questions here, and we'll just walk through how to solve these things graphically. Okay, let's take a look at some questions here. So, solve the following rational equations, and we're going to round to the nearest tenth. Okay, well, here we go. Well, this one has already been moved over to one side of the equation, so this one's actually going to be pretty straightforward for us to work on. Let's maybe zoom in a bit here. So, y equals, and I will make this x plus 6 divided by, and I got to make sure I put parentheses around that denominator or the calculator won't understand what I'm dividing by, minus 5. Okay? I'm going to graph that, and I've gone back to my regular zoom settings here. Okay. And I've got an x-intercept there at what looks like -1, and another one here at what looks like, 4. But let's use the calculator to figure those out here. We're looking for zeros in this situation here, so 0. And I'm going to move my cursor just to the left of that point of intersection right there, or that x-intercept right there, press enter. Now I'm going to move it to the right, and what I need is that x-intercept now to be between those two triangles, between those two lines. And when I press enter, it jumps, and there we go. Whoops. You can see the answer there is -1. So x is equal to -1 is one solution. Now let's go find the other one. Looking for 0, so now we're going to come over here. I'm going to leave my cursor just to the left of it. Move my cursor over, just to the right of it, press enter. So as long as that x-intercept is in between those two triangles, between those two lines, don't worry about the guess, just press enter to get past it. And we get 4. So my two solutions there are going to be -1 and 4. Let's take a look at B. Okay, this one is actually set up right now for us. Now we could go both ways on this one. We could bring everything over to one side or leave it split up. And actually in this particular case here, because of how that works, I'm tempted to leave this split up. So let's put those on both sides there. So now I'm going to graph 2x divided by bracket x plus 3 plus x divided by x bracket x minus 3. Again, I got to make sure I put parentheses around that denominator. And then my next line, y2, is going to be 18 divided by x squared minus 9. Okay, let's take a look and see what it looks like when I graph it. Okay, so there's the left side of the equation. And there's the right side of the equation. Now, look at that. Now, I can clearly see a point of intersection right there. Okay? But, man, I'm not clear on some of these other points of intersection, so I'm going to have to play with this a little bit. Like, it might be that there's a point of intersection here. So let's do this. We're going to look for the intersect here. I'm going to move the cursor over. I want the cursor to be over here a little bit. Okay, so I can see the cursor right there. I'm hoping that it's going to jump up here and find something. So I'm going to press enter. It jumped to the next curve. I'm going to press enter. Calculator's thinking, okay, no sign change. So now what that tells me is that, whoops, on this side of that asymptote, there is no point of intersection. Okay, let's take a look and do that again. So let's move the cursor over. There it is. Now, I can't tell if there's more than one point of intersection here. Like maybe the curve is such that it's cutting through that red one twice. I don't know. So let's leave that low, press enter, go past the guess. Okay, and it jumps me up to -2. So I'm getting one solution here at -2. I don't know if that's the only solution. Okay. Let's take a look over here. Let's see if we can find one over a little bit further on here. Does it look like they intersect again over here? Whoops, no. Enter, enter, enter. Oh, did you see that? I was over here looking to see if it intersected over here, and it jumped over here. Now that suggests to me that there's only one point of intersection in between the two asymptotes. Let's go try this again, intersect. This time I'm going to move over this asymptote on the right, because there might be a point of intersection here. Enter, enter, enter. And it jumped me back to here. I wasn't expecting that. So I'm only getting one point of intersection here. Now, I don't know if that feels right. Okay? So let's do this. Let's go back to y equals. And I'm going to drop this one right here. And I'm going to move that up to here. And I'm going to make this -18 divided by bracket x squared minus 9. And what I'm doing is I'm applying that rule that I used for the previous question here. And when I press graph here, and I'll explain why I'm doing this in just a second here. Now, when I do it this way, I am looking for x-intercepts. Well, now I can clearly see that there's only one x-intercept, and I feel much better about that as a solution. When I did it the other way, it works. It totally works. But the graph can get messy. This is a great example of that situation there, okay? So if you want to clean that up, all you got to do is bring that one, like that right-hand side to the other side here, the left-hand side, and then just look for the x-intercepts. Okay, now let's finish it up by looking at this one. Okay, now let's try it again. Let's try the left side, right side, see if we can make this one work here. So 3x minus 1 divided by x plus 4. Whoops, got to make sure there's brackets around the numerator and denominator. Plus 3. And then this is going to be 6 divided by x minus 4. Whoops, x minus 4. See what we get. Okay, well now I've got two really clean points of intersection. That one actually worked quite well. So now I can move the cursor closer here, press enter, enter, enter. All right, to now this one, the numbers are working out a little bit more not pretty. So negative 2.1. I'm going to do that again. Second trace. Intersect, and then we're going to move over to this next point. Now I want to make sure that I cross over that asymptote. Although in the previous question we saw that the calculator did jump backwards over that. I'm just not convinced that that'll always work. In this case, what do we got here? 5.3. And those are your two solutions.